is... Are we frozen or are we not frozen? We're not frozen. This is week 8, lecture 0 of CS50DC. And today I'm going to start by asking for some help. I basically recorded a set of results from some tests that I did with some of my students, and I've recorded all the results here and put all of the results in these jars. And I need help to find out whether anybody actually got the score 18. So can someone please come and help me, because I'm really struggling. Matt, come and give us a hand. I know you've already got a rubber duck, but if you want to take another one, there's one there. So Matt, just stand here for me. Now, basically, I stored everyone's results in these jars. Now, I want to know, is the score 18 in there?
Yes.
Yes, it is. How do you know it's in there?
I can see it there.
Because you can see it.
Yeah.
So when you look at these jars, when you look at all these results, you just instinctively saw 18.
Yeah.
And it was there. Okay, that's cool. So basically what you did is, if we have a look at the board, you saw these jars laid out like so.
Yeah.
You were able to, as a human being, look at all of them and instinctively see, well, there is the number 18. Is that thing? So can you take the number 18 out of the jar for me? Fantastic. You went straight there, held it up to the camera, and we've got 18. Brilliant. So Matt, if you just bear with me 1 minute, I'm going to take all of these out, like so. And what I'm going to do is, this time, I'm going to put them in the jar, but I'm not going to let you see them.
Right.
Alright, so they're the same numbers, so bear with me on that. They're the same numbers, but I'm going to put them in the jar so that you can't see them. Alright, so if you just look away for a second, bear with me. Right, so I'm facing them down now. And this is kind of like a computer's memory in a sense. I can store these numbers inside the computer's memory, but we can't actually see them. We can't dig into the computer and see them. So if I want to know whether the number 18 is inside the computer's memory, I'm going to have to come up with some sort of algorithm to find out where it is. So Matt, you just turn back round. So this time, if you come and stand here, and we do the same thing again. So you're looking at these jars, you're looking at the memory inside the computer, and I'm saying to you, I know the number 18 is in there, well, I think the number 18 is in there. Can you go and find it for me, please? Now, just before you go, if we just illustrate this here, again, they're just empty jars. Yeah, we can't see them, but there is things in them. So inside the computer's memory, I'm trying to illustrate it here, there is something in there, just like there is in these jars here. So, Matt, can you talk us through what you're going to do?
Well, I would look into this jar and
Yeah?
I would look and I'd see that is
What number is that?
27.
27. What are we looking for?
18.
So is it that one?
No.
So what are you going to do next?
Go to the next one.
Oh, you're going to go to the next jar.
To the next one. And that's 11, so I'm not going to go for that. Go to the next jar, it's 23, so I'm not going to go for that.
Quite long-winded, isn't it?
32, go for that. 18.
Oh, we found it. Okay, thanks, Matt. Thank you. Do you want to grab a drink and take a seat? Round of applause for Matt. We found it. Excellent. So, Matt, what you did there is you went through one by one and looked inside the memory of the computer and then compared what number you were looking for against that single part in memory. Just to change this slightly, I'm going to put these back in, and Matt, if you were to do this again, let me just count how many steps that took you. That was 3, that was 4, it took you 5 steps. Now, just so that this works with my slides, you could have come through and done exactly the same, but you could have done it going the other way. You could have started at the left and gone that way, okay? So what we're doing here is we're conducting a linear search. We are literally going from the start, comparing to the next one, comparing, going to the next one, comparing, etc. So if I illustrate this on the board, what you did is you went to the first one, checked whether that was the number 18, and it wasn't. So again, illustrating that. Oh, that's the number 35. Yeah, it's not that one. You then went to the next one, and you checked it again. And oh, that's the number 9, and it wasn't that one. And then you went to the next one, and oh, we found it. And it was just lucky that in this example, when I go from left to right, as opposed to right to left in this example, it only took me 3 steps. But it actually took you going the other way, it took you 5 steps. Yeah? Now, what could possibly be the worst case scenario for that search that you implemented, Matt?
That the 18 was in the far
yeah, when you did it here, that the 18 would have been here, and when I do it in my example here, the worst case scenario would have been that the 18 would have been there. And how many steps would that have taken me then? 7. I've got 7 jars, so it would have taken me 7 steps to get to the ideal number that I'm searching for. Okay, so we're going to talk later about the efficiency of algorithms. This algorithm works. You went through it one by one and were able to compare your number against the number that's in memory, and we eventually found it. But again, we can have a look at this and start thinking of, well, if there's 7 jars, the maximum it's going to take these 7 steps. But what if there's 1,000,000 jars, and the number that I'm looking for is right at the end? Well, then it's going to take me 1,000,000 steps. So what if there's 2,000,000 jars? Again, so we can see that ideally a linear search works, but it's not necessarily going to be as efficient as we want it to be, especially when we're working with large amounts of data. Yeah. So the concept is that we go through one by one, and the worst case scenario would be that it would be at the end, thus it would be 8 steps. Now, if I was to code something like this into the programming language C, I might start by writing some pseudocode. So I want to construct an algorithm that goes and has a look inside an array. So an array, if you remember, a string is an array. It's just a sequence of data stored next to each other in memory. So if I wanted to pseudocode this up, I might say for each element in the array, so this is my array, for each element, each one of these is an element in the array, if it is the element that I'm looking for, return true. So I go in, this is the first element, is it the one I'm looking for? No. Next one, is it the one I'm looking for? No. And when I find the one that I want, I would return true. Okay. Just a quick sanity check here, because when I was looking through this algorithm as well, someone might want to write that, okay, so if it's not the one, well then return false, and then go back up again and check it again. Why is that not correct? What problem will I encounter if I were to code it like this? As opposed to, this is correct, this is not correct. Think about what return does. What does return do? It returns true. So if I go into the first element, and if it's the element that I'm looking for, return true, what's going to happen if it's not the first element? If it's not the first element in the list, so this statement here, this if statement, imagine that it's not the first element that I'm looking at, so therefore it does not execute this code. What's going to happen?
It will return false.
It will return false, so it will go to the else statement and return false. Now, if this was within a function and I return false, then I come back out of the function and I return false. Yes? Why is that not good in this sense? If this was in a function here and I was returning false, why would this not be ideal? Anyway, well, think about it. If I'm going to the first element in the array, and that element does not meet this criteria, so that element that I'm looking at here is not the number that I'm looking for, then the else statement will kick in, and it will return false, which means it will literally only check the first one, and then it will return false. It's not there. Now that's not what I want to do. I want to keep going until I find them, and then if I don't find it, return false. So what I could do is actually remove this else and take away the indentation here from the return false line and put it in level with the for here. Okay? That was a little bit of a sanity check that some of you might encounter later on when you start programming this. Okay, so that's the correct pseudocode that I would implement for this algorithm. Now, I'd like another volunteer, because this isn't ideal as we said, so would anyone like to come up? Harry, would you like to just come up and help us with this one?
Yeah, sure.
Yeah. Okay, so Harry, what I'm going to do is, when I laid maths data into this array, when I put them in, I didn't tell him whether I'd sorted it or whether I'd just literally placed all the values in there, right? So what I'm going to tell you is that I'm going to put a new set of numbers in these jars. I'm going to put a new set of numbers in this array. But I'm going to tell you that I'm going to sort them. Now, if you saw what Matt did, he went one by one by one by one by one until he found the number that he was looking for. Now, I'm going to sort the numbers, and I'm going to put the smallest one here I'm going to put the largest one here. And I want to see if you can think of a better way to actually find the number that we're looking for. Okay, alright, so if you just turn around whilst I put these numbers in the jar. So you're not going to see them, but you know that they're sorted the way that you're looking at them left to right. And I'm going to tell you that the number that I want you to find is the number 50. Okay,
No.
Harry.
Yeah. Right.
What do you
Do I
think?
know which one's my lowest number?
You don't know which is your lowest
Okay.
number, no.
So, do I know which side's lowest and which side's highest?
We know that they're going to start here and end there.
Okay. So I'm going to take. This would be my logic. I would look this number, and then I'd go to this side.
But look, show them what numbers you've got. We first picked up number 26, and then we happened to find the number 50, which was lucky.
Yeah.
In a
See,
sense.
I would kind of try and like bisect it. You know what I mean? I don't know, and then like find. I don't know. Is that might not be the right logic? Though.
Well, no, I mean, did it work? Did you find the number you
Oh
wanted?
yeah, it did. Yeah.
Okay, but what was the worst case scenario? What if the number 50 wasn't there, and it
It
was...
could have been right in the middle because I was gonna. Actually, I don't know. Is that a logical way? I was gonna work from either side.
Okay, so let's just change this. Let's just put this here.
Yeah.
Let's imagine that this was the number 52. Let's have a look at this. Imagine this was the number 52.
Yeah.
Okay, so do that again. And let's have a look at that again. So what would you do? You take the first one out.
Take the first one out.
So you know what you're dealing with as the
small.
smallest.
Yeah, that's our smallest.
Right.
Then I take my highest out.
And it's 52, let's imagine.
Yeah.
Now
so
what would you do?
52. Now, actually, yeah, no. So I wouldn't go straight in the middle. I think I would. Actually, I'm not. A computer is different, but I would make the judgment of which side is closer to my number. So if this was 52,
Yeah.
I would then the next one I'd pick would be kind of
Closer to that side.
closer to
So
that
if this
side.
number was 75, in theory, you'd probably go back to the middle, wouldn't you?
Back to the middle, yeah.
Okay, all right, that works nice. Would anybody go about this slightly different? Thank you, Harry. Take a duck if you haven't got one. Robbie, do you want to come and have a look at this and see how you might go about doing this problem, or solving this problem? So have you got a different sort of logic to this?
I did the same thing to start off with, so I picked the first two.
Swapped them back round, but imagine that was 50 there. I'm intrigued. Okay, so imagine that was 52.
So I'd say this number's too small, that one's too large.
Yeah.
So I'd go and put these back,
Yeah.
go into the middle now, pick up this one.
Yeah.
See, this is 42,
Yeah.
so this is smaller,
Yeah.
so I know it can't be any of these. So I then go into the middle of these,
Yeah.
although there's only two. If there was a third one, I would have gone to the middle there.
Okay.
I know that that one was 52 and that one was 46, so it's closer to 52. So I'll go with the one on the right, and then I find 50.
Okay, that's interesting. That's interesting. Thank you, Robbie. Take a duck if you want. Now, I'm just going to try and link you back a little bit to one of the very first lectures that we did with a dictionary. Now, in a dictionary, the problem that well, not the problem that we're having, but what we're not getting across here, what I'm trying to get across is that for those two that came up and looked at this, they wanted to know what the lowest item number was, and they wanted to know what the largest item number was. If we look at a dictionary, or we look at a phone book, and we said that we wanted to find someone like Mr. Smith, now, do we need to go and have a look at the phone book and have a look at the first page to know where it starts, and then go and have a look at the last page and see where that starts? Do we need to do that? No. Why do we not need to do that?
Because we know it's in order, so we just go to S.
Right. So we know that the phone book or the dictionary is alphabetically sorted A to Z. Yeah, we just know that. Well, in theory, don't we just we know that this is sorted? Does it really matter which one's low or which one's high? As in, which number is the lowest or which number is the highest? If we think of the concept of the dictionary and we just know, okay, we know that A is the lowest, but we just know that's the lowest, and we Z is the highest, but in theory we just know that's the highest, and we're just going to go straight down the middle. We're going to go straight down the middle and see how far we are or closer to S. So I'm going to implement that now. Okay, I'm going to do it on the board instead because I think these jars might be difficult to see. So imagine this. Imagine that again, we've got the same scenario that we had here on the table. I've sorted them left to right in ascending order. What I propose is that in theory you don't need to actually check which is the lowest number and which is the highest number. You can just go straight to the middle. Because if you think about it, when Robbie did it, he checked that this was the lowest, checked that this was the highest, then he went to the middle, and that's 3 steps. I propose that if you just go straight to the middle, and it's 42, and you know you're looking for 50, like Robbie said, is you can literally get rid of all of these and know that your problem or the number you want is just within here. And then you do the same again. You go to the middle, and you know that the number you're looking for is higher than that, so you can get rid of all of these, and we found our number. So actually these first two steps weren't necessary. I understand why you wanted to do them, but actually we can remove those first two steps and go down the same method, and we'll get there. And this, if I had 7 items, it actually only took me 2 steps until I knew where that number was. If that makes sense? It took me 2 steps and I knew where that number was. It was the last item actually. And this is called a divide and conquer algorithm. We are literally halving the problem each time we iterate through this repetitive sequence of steps. Half the problem, find the middle one. Half the problem, find the middle one. And this is called a binary search. We're going to later talk about the efficiency of this algorithm, but this is a binary search algorithm, and that is how it works. Now, I think actually this would be a good time to introduce Magister to go into this. I think we've covered this enough. They're the 2 different searches that you're going to have to know about in order to solve this next problem set that we're going to give you over the Christmas period. Okay, but in order to talk about, right, well, which one of those is more efficient, I think we can see which one is possibly more efficient under circumstances. But now in terms of actual efficiency, we're going to hand over to Magister, and he's going to talk about big O and a new O.
Okay, so when we talked about these searches, binary and linear, we said that the binary search would take 2 steps when there were 7 items in there maximum. Well, I could say that there's actually more than 2 steps. There's 1 step here where I go to a specific jar, then I read the number and compare it to the number that I'm looking for, and then I move to the next jar. I could say that's 3 steps. I could define that as 3 steps. Or I could just as validly count each thing as 1 step. And we don't really know how we define our steps in this situation. We don't know whether each movement counts as a step, each time we pick up a paper counts as a step. So what I've decided is that for the linear search, if we have n items, it's going to take 3 n steps. I've decided that this counts as a step, this counts as a step, and this counts as a step. So taking the number, comparing it, and then moving to the next number. I've said each of those counts as 1 step. So our linear search could take up to 3 n steps. It could take, for these 7 jars, it could take 21 steps. And similarly, for the binary search, it could take up to 3 times log n plus 1, because log n represents, if you haven't studied this in math yet, it represents what you need, what power you need to raise 2 to get n. So in the case of, let's say, 8 jars, log n would be 3. Log 2 of n would be 3. So if we're dividing the problem in half each time, that means that if there's 8 jars, we can only divide it in half maximum of 3 times. That's why the binary search has this concept of log in it. And again, we've said the 3 because I've said that each time we go to a jar, compare it, and then move to the next jar, I've counted that as 1 step. And I've added an extra 1 step here because if we have 1 jar, it's impossible to find the item in 0 steps, so I've added a plus 1 there. But then again, someone else could have added a plus 3 there because they could have thought that actually you need to do all 3 steps for the first jar. So it gets kind of confusing when you're defining these, the number of steps it takes for these algorithms. And by the way, you can drop the base 2 because in computer science we always deal with log in terms of the base 2 log, since computers run in binary rather than base 10. So log in computer science is implied a log base 2. It gets confusing when we try and define what the number of steps actually are. And if we look at this graph, what we can see is, well, the real difference between an algorithm that runs in 3n steps compared to an algorithm that runs in 3 log n plus 1 steps is the shape of the curve. If you look at that n and n over 2, when we saw this graph back in the beginning, when we were looking at the dictionary and skipping 2 pages rather than 1, they are different curves. The yellow one is obviously going slower than the red one. and yet they're the same shape. They're both straight lines. Whereas this log n curve is a completely different shape. It's much, much flatter than the other two. And we, in computer science, need a way to capture this. We need to capture the fact that there are different speeds of growth of algorithms. It doesn't exactly matter how many steps this algorithm takes, because the most important thing about this formula is the fact that there is a log n in it. And we capture this in computer science with the concept of big O. So this algorithm, binary search, runs in big O of log n. And big O, you can take it to mean on the order of. So it doesn't take exactly log n steps. In fact, we've gotten rid of the 3, the coefficient 3, and we've gotten rid of the 1. So it runs in around log n steps. What that actually means is that as n increases, the amount of time will increase in terms of log n. So if we double the number of jars here with binary search, the number of steps is only going to increase by a factor of 1, basically. It's not going to double the number of steps. And similarly here with the 3n steps for the linear search, we can say it's big O of n. It's on the order of n steps. And there's lots of other running times that you can have in terms of time complexity of algorithms. We'll see some big O of n squared algorithms in the future, and some n log n ones as well. Big O of n, of course, we saw this linear search. Big O of log n, the binary search. Big O of 1, what could that mean? Any guesses? So big O of 1 represents that the algorithm runs in constant time, no matter how big the size of the problem is. Any examples of algorithms we've seen that could run in constant time? So imagine printf. That'll always take the same amount of time. You could give it a string of length 5 or a string of length 50. It would still print it out instantly. So we could say that print is a constant time algorithm. And the formal definition of big O is some mathematical definition which you can go and look up. But the essence of big O is that the big O, the thing that's inside the big O, represents the shape of the curve. So big O of n algorithms grow in a straight line. We don't care about whether the straight line is pointing like this or like this. We care about the shape of the line. Big O of log n algorithms grow like this with the size of the problem. We don't care where that curve is or what exact shape it is. All we care is that generally this is the shape that algorithm follows. And we can see that at some point, no matter what kind of linear line this is, whether it's really flat, at some point the log n is going to be less time than the linear, than the straight line. And that's why we don't care about the specific number of steps or the specific number of seconds, the specific number of array indexes or comparisons. All we care about is the order on which those operations occur, the order of n on which the time grows. And this concept of big O, we will see more next week when we talk about how we would actually get this array into a sorted situation. And in order to compare different algorithms, like we kind of know that binary search is better than linear search, but we use big O as a formal way of defining which algorithms are better than others. And the thing with big O is that it's an upper bound on how much time this algorithm could take. Because we saw that if we did a linear search and we checked here first, and the item we were looking for was the first item, this has taken 1 step. It hasn't taken me 3n steps. It hasn't taken me 21 steps. Or you could say it took me 2 steps because I looked at it and then compared it to the number in my head. So the algorithm won't always take 3n steps, or it won't always take on the order of n steps. But the big O is the maximum for what it could possibly take. In the worst case, let's say, in the worst case of linear search, I could be taking n steps, or I could be taking 3n steps, or I could be taking 3n plus 3 steps. But on the worst case, the steps that I take are on the order of n. And that's basically it. That's what we're going to talk about when we say big O. When we encounter big O, when we look at more complex algorithms, and we have to analyze their running time, their complexity, whether they're efficient, we can use this measure of big O to define how efficient an algorithm is without necessarily worrying about the exact number of steps that it takes. And that's basically it.
I'm just going to go over, I'm just going to come back, if that's alright, and seeing as we've got a little bit of time left, as Mataza has said, we don't really care exactly about how many steps it takes to do something. But I just wanted to give you an example of, in case there was some lack of clarity in terms of what log 2n is. I'm just going to give you a little bit of clarity on that. Like Mataza said, when we talk about log, in mathematics we might talk about the fact that the base is always 10. But because we're computer scientists, when we talk about log, it's always in base 2. So I'm going to just put this little problem on the board. And this is a nice little game that I play with my year 8s. And they're amazed that I can tell them exactly how many steps it's going to take. So what I tell them is I said, right, I'm going to ask you to think of a number between 1 and 1,000. And I can guarantee that I will get your number in 10 guesses. And they're amazed. They're like, how is that possible? How, surely it should take you 1,000 guesses. Well, no, I can guarantee as long as you tell me each time I guess whether the number that's in your head is higher or lower than the one I've just guessed. And the idea of that is, like I said, it's a divide, and I'm using a divide and conquer algorithm. Every time I guess their number, I can halve the number. And it does actually amaze them a little bit. So I just want to give you this example. If I ask you to think of a number between 1 and 8, I can guarantee it will take me a maximum of 3 guesses. A maximum of 3 guesses before arriving at your number. In fact, in theory, as we said, we could actually say, depending on how many, like we're counting, how we're counting the steps, I could say, well, I'll know your number after 2. Okay, so we'll just illustrate that. So think of a number between 1 and 8, and imagine that your number is 8, all right? But I don't know that. Okay, so imagine your number is 8. What I might do, in fact, what I will do if I use the algorithm that I want to implement and the one we've just talked about, is I'll go for the middle number. I'll say, right, I know it's between 1 and 8, so I'm going to guess your number's 4. Now, obviously, what they will do is they will say, no, my number is higher than that, which will leave me knowing that it can only be 5, 6, 7, or 8. So my next guess would be 6, because I go for the middle number. When I say I go for the middle number, I can, in theory, choose any of these. Yeah, but we would tend to use the first one. And that's because we'd use floor division to find out what the middle is. Okay. So I then guess 6, and they'd go, no, my number is higher. So then I would know it's either 7 or 8. Now if I guess 7, and they say, no, it's higher, well, then I know it's 8. So it's taken me here 3 steps to get their number, which is 8. So if I have a look at how I work that out, how did I know it would only take me 3 steps? And it's all about what we talked about with regards to log n. If I can look at the power of 2 to 3, yeah, 2 to the power of 3 is 8, and therefore the number that I am looking for is 8. So if I have a look at the log of that, it's 3. So I know it's only going to take me 3 steps. Now, for example, if I wanted to say guess the number 1 to 125, give me a number of 1 to 125, and I'm going to guess it, well then, I know that I can't guess it in 6 steps. But I know that 2 to the power of 7 is 128, so I can guarantee that if I use this algorithm, I can guess your number in 7 steps. So it will only take me 7 steps up to 128. Now, if I wanted to go even bigger, which is the one that I use with the students, and I say I'll guess a number between 1 and 1,000, I know it's only going to take me 10 steps, because 2 to the power of 10, which is the log, is 1,024. So that's a little bit more clarity on what we're talking about when we say log n. But again, as Mataza said, when we're measuring the efficiency of these, the number of steps really isn't that important. It's just knowing about that graph and knowing the shape of those lines on that graph in order to measure its efficiency. Okay? Alright, so tomorrow we've got another lecture. We're going to be talking about sorting algorithms, and that's going to be with Will. But for today, that's it. That was week 8, lecture 0 of CS50DC. Thank you.